Hi everyone and welcome to today's Physics Daily Booster. What we're going to be doing in today's booster isn't explicitly listed on any of the advanced information for the higher or foundation physics. However, as we found out from earlier exams, that doesn't mean there won't be questions on it. So still relevant to make sure we know this stuff before going in. To start off then, what we're going to do is have a little look to see what happens when we put two of these fields together. So if we've got a current carrying wire and we place that inside another magnetic field, those two magnetic fields we've got are going to interact, because remember, the current carrying wire creates its own magnetic field. So putting two magnetic fields together, they are going to interact. And by interact, what we mean is those two fields are going to push on each other and it creates a force on the wire. The direction of that force on the wire will always be at right angles to the magnetic field. What we're going to see then is that if those two fields are in the same direction, then they're going to add up. If they're opposite directions, then they're going to cancel each other out. What we're actually going to create then, if we look at this example where we've got a piece of wire with a current flowing through it and a magnetic field here in a magnet, when we put the two together, we create this thing called a catapult field, because what we're actually doing is by placing the wire in there, which is our little circle with a cross in it, then we're stretching those field lines. So you can see how they've been stretched up around it. As a result, we're going to inflict a force upon the wire, and the force is going to act downwards in this example where the red arrow is pointing, because it's going to be moving in the direction that shortens the field lines. So they've been stretched upwards, therefore the wire is pushed down to shorten them. Which brings us on to how we work out what direction this thing's going to move in. Left hands, hopefully we know the difference between our left and our right for this. It is Fleming's left-hand rule. Just knowing the name Fleming's left-hand rule has got you a mark in previous papers. So in order to work out the direction of the force that acts on a wire in a magnetic field is Fleming's left-hand rule. So you need to set your hand out like the lovely picture there shows us. Your thumb is going to be the direction that the wire is going to move in. Your first finger is going to be pointing the field, so north to south, the palm of your hand being north, the tip of your finger being south. And your second finger is the direction of the current. So you've got to point in the direction the current is going. Because we have exams as a two-dimensional thing, they've tried to draw these pictures three-dimensionally, but it's not always easy to visualize. So what we've got on the right is one of the kind of pictures that you could see. So first thing you need to do is get your hand pointing from north to south. So in this case, the palm of your hand should be where the north is, your first finger pointing out towards south. Then we've got to work out where the current is going. Now in this case, it's traveling along the wire in that direction and then into the paper. A much straighter path than I've drawn there clearly. So what we need to do is you're going to turn your entire hand upside down, because your second finger has to be pointing into the screen in this case. Because of that, your thumb is now pointing downwards, so that bit of wire is going to move down. If obviously the current was coming out towards us, then your hand would be the opposite way around and the wire would move up. These are usually quite straightforward in the fact that you could even hazard a guess as either up or down as the options. If you can't work it out, pick one, up or down, and then write that, but hopefully using Fleming's left-hand rule, you can always work it out. We then have a calculation. So again, this is on your formula sheet. The force on a conductor carrying a current in newtons, because it's a force, is your magnetic flux density times current times length. Key thing to look out for here is obviously make sure that your length is in meters. If it's in centimeters, divide by 100 first of all, and then you could rearrange if you need to. But what that tells us is that the force is going to depend on the current, the length, and the magnetic flux density. This now leads us on to something that we're going to be looking at in more detail throughout this topic, the idea of if we've got a loop of wire and we place that in a magnetic field and allow a current to flow through it, then what we're going to end up with is opposite forces on the two sides. So if we look at the diagram on the left here, first of all, what we can see is on our loop, we've got this side, the current is coming out, and on the opposite side, it's going in. So that tells us that the two sides of that coil are going to move in opposite directions, one up, one down. Use Fleming's left-hand rule, and you can see that it's going to move up on the left, down on the right. So it's going to spin at that point. When we now consider what we need to do to ensure that coil can spin continuously, we've got to make sure that the current is always travelling in the same direction on the right and the same direction in the left. Otherwise, what we'll end up with is it would only go so far. Now, the way that we can actually achieve this is through the use of a bit of equipment called a split ring commutator. So as the name suggests, it's a ring with a split in the middle. You've got these two gaps at the top and the bottom. So what we've got is a little semicircle connected onto the coil wire there, and then they sit on those little contacts to the power supply. What we'll find then is that as this whole thing spins, then it's going to disconnect on the gap. So when the gaps are next to our contacts, obviously it has no connection, but because we've got momentum, it just keeps spinning. And then as it makes contact again, it will make sure that the force is always in the same direction on that particular side. Which leads us beautifully onto how motors work. So when we're looking at our motor, we have our split ring commutator, as we can see in the picture at the top, coil of wire, and then on this case, the left-hand side will always be moving upwards, the right-hand side will always be moving downwards, so it's always going to spin in a clockwise direction. In terms of how we can change the speed of a motor then, quite simply, we could change the magnitude of the current. You can change the strength of the magnetic field, change the number of coils in the wire, or change the length of the coil. Now, if they ask you how you can increase the speed of a motor, then obviously make sure you say increase the magnitude of the current, increase the strength of the magnetic field, etc. If it just says change, you can just literally write magnitude of the current. But if it says how do you increase, make sure you do apply that correct pattern. If there are bits you'd like to see in more detail, you can obviously use the video on the main part of our channel. You could use your revision guides to support you, and as always, I do recommend having a look at some of the old physics papers just to see the style of questions that come up. And then of course, don't forget to join us again tomorrow for our next Daily Booster for Physics.